Welcome to the deep dive. So if you've ever asked, what is an LLM, and just got a bunch of different answers, maybe chat GPT, or billions of parameters, or even just a confused shrug, well, then this deep dive is definitely for you. We're aiming to cut through some of that noise today, because let's face it, for a lot of people, how these large language models actually work still feels a bit more like magic than mechanics, and we want to fix that.
That's absolutely right. I mean, we're living in a world where this LLM AI is kind of quietly running behind the scenes in so many places. Think about those smart reply options you get in your email, or maybe code snippets from GitHub Copilot, even the voice assistant on your phone, the one that somehow gets your accent.
Yeah.
Yeah, it's often got an LLM inside.
And knowing what an LLM actually is, well, it helps you make some pretty important calls, right? Like when should you trust the answer it gives you? When do you absolutely need to double check its work? And sometimes when you just need to laugh because it's giving you a totally confident but completely wrong hallucination, as they call it.
Exactly. Hallucinations are a real thing.
So our mission today is pretty straightforward. We're going to unpack this whole complex topic, give you a shortcut maybe to feeling, genuinely well-informed about it.
Yeah, we'll try to pin down what an LLM is. We'll use clear language, try to keep the jargon manageable. We can walk through its history, which is actually quite surprising, peek under the hood a bit, see how it goes from, say, tokenization all the way to predicting the next word. We can even touch on the software and, crucially, the chips that make it run, and reveal that sort of three-stage training recipe people use, plus highlight how critical data quality is something often overlooked.
And yeah, we definitely need to talk about the energy side of things. These models have a massive footprint, so we'll look at that and maybe discuss some greener ways forward. Get ready for, hopefully, a few aha moments along the way. So to kick things off, at its absolute core, what is a large language model?
Okay, probably the shortest, simplest answer. It's basically a neural network that's really, really good at guessing the next bit of text. And then it just keeps guessing the next bit and the next until it decides it's done. But these aren't random guesses, not at all. They're shaped by patterns the model has learned, soaked up, really, from vast amounts of text. Pretty much everything people have written online, books, forums, research papers, code, you name it.
Okay, so it's kind of like autocomplete, but like autocomplete on steroids, scaled up massively.
Precisely. Yeah, think of the autocomplete on your phone, right? If you type the capital of France is, your phone probably suggests Paris. Now imagine that same basic idea, but instead of your phone's little engine, it's the size of a jet engine. And it remembers trillions of words. It can juggle logic puzzles, translate languages, even riff on, I don't know, Pascal's wager, maybe crack a joke.
Yeah.
That massively oversized autocomplete, that's the heart of an LLM AI.
That's a huge leap, though, from just suggesting the next word on my phone. How does it technically get that smart? It's not just looking things up in a giant dictionary, is it?
No, not at all. Well, technically, an LLM is a specific type of neural network, usually what's called a transformer. And it's packed with billions, sometimes even trillions of these adjustable numbers. We call them parameters. Think of those parameters as like tiny knobs and dials. The model adjusts them during training. So going back to your example, the probability for Paris gets turned way up, and the probability for, say, banana gets turned way down. And that transformer architecture itself, that was the big breakthrough from 2017. It lets models handle really long stretches of text very efficiently by paying attention to the relevant parts all at once.
Oh, okay. I've heard people call LLMs stochastic parrots. What's that nickname about?
Yes. The stochastic parrot. It points to a maybe uncomfortable truth. The LLM doesn't understand your question like a human does. It's essentially mimicking patterns it saw in the training data, patterns that look like understanding. So it's stochastic, meaning probabilistic or based on guesses, and parrot because it's repeating or reassembling things it's seen, often without comprehension. This parrot thing is why those confident but wrong hallucinations happen. It's not really a bug. Sometimes it's just inherent to how they work. But, I mean, it's turned out to be an incredibly gifted mimic. So good, it helps doctors write notes now or let students, outsource their homework. Yeah, that's why there's so much public buzz around LLMs and generative AI.
Right. And speaking of buzz, let's talk history, because
Yeah.
it really does feel like LLMs just sort of exploded onto the scene very recently.
It does feel that way. Though, if you ask an AI historian, they might start way back in 1966 with Eliza. Remember that? The chatbot therapist program. It was simple, but it tricked people into thinking it understood them. But the real, rocket fuel moment, that was 2017. When Google researchers published that paper, Attention is All You Need, that introduced the transformer. That's the foundation for pretty much all modern LLMs.
Wow, 2017, that's really not that long ago for something having this kind of impact.
No, it's incredibly fast. So quick timeline, 2018 OpenAI releases GPT-1, Google ships BERT. That really kicked off the large model era. 2019, GPT-2 comes out,
Right.
1.5 billion parameters. That was the first time many people saw AI generate text that was, shockingly coherent, a big step up. Then 2020, GPT-3 arrives, 175 billion parameters. That's when people really started asking, what is an LLM? Because it could do so much more, like write decent essays.
And then, of course, ChatGPT. That felt like the moment everyone suddenly knew about it. Millions of users almost overnight.
Absolutely.
Yeah.
Late 2022, ChatGPT drops with that super easy chat interface, hits 100 million users in, 2 months? Just phenomenal growth. Then 2023 rolls around, GPT-4 goes multimodal, handles images,
Yeah.
not just text. And then everyone jumps in. Google with Gemini, Anthropic with Claude, Meta with Llama, lots of open source models like Mistral and Falcon 2. The field just exploded.
So what about more recently?
Yeah.
Say 2024, maybe looking into 2025. What's been happening?
Yeah, these last couple of years have seen some big jumps. Context windows, that's how much information the model can handle at once. Hit like 1 million tokens, even 2 million. So they can process huge documents now without forgetting the beginning. Hallucinations seem to be dropping, though still an issue. Reasoning capabilities are definitely getting better. Plus, you're seeing voice, image, and this idea of tool use all merging together. It feels much more seamless. Each jump, more parameters, more data, new training tricks, just widens the gap between what these models are now and what they were just, say, 5 years ago. Now we're leaning on them for stuff like summarizing research, drafting legal docs, debugging code, things that used to take hours and lots of coffee.
Okay, this incredible growth, this scale,
Yeah.
it obviously needs some serious horsepower behind it. How do you actually build one of these? It sounds like you need supercomputers and very specific software.
Well, yes and no. I mean, you could actually prototype a small LLM in an afternoon if you have a decent GPU and know your way around something like PyTorch. But scaling that tiny prototype up to something that competes with, say, GPT-4, that's a whole different ballgame, a massive engineering challenge. Engineers mostly use Python for the general coding and trying things out. Then frameworks like PyTorch, TensorFlow, or JX handle the really heavy-duty math, the tensor calculations.
Right, and for the really massive models, the ones with billions or trillions of parameters, how do they even manage to run those?
Yeah, for that scale, you need specialized libraries. Things like Megatron LM, DeepSpeed, or PyTorch's own FSDP. These help chop up the model and the data across potentially thousands of GPUs working together. And for just grabbing pre-built components or models to start with, Hugging Face Transformers is like the go-to resource for almost everyone. But the raw number crunching, the matrix multiplications at the very core, that happens on incredibly powerful specialized hardware. Think NVIDIA's H100s or newer Blackwell chips, Google's TPUs, their tensor processing units, and AMD's MI300 series chips are big players too.
Sounds incredibly expensive. I've heard the compute cost, the electricity bill basically for training these things is just astronomical.
Oh, it is. Astronomical is the right word. Training GPT-4, for instance, reportedly cost tens, maybe hundreds of millions of dollars just in compute time and electricity. That huge cost is a major reason why most open source models tend to top out around, say, 70 billion parameters. They often rely on clever fine-tuning methods to get good performance without needing $1 billion training budget. People use all sorts of tricks to make things more efficient techniques like mixed precision training, quantization, parameter-efficient methods like LoRa, or architectures like Mixture of Experts, MOE. It's all about squeezing more intelligence out per watt per dollar.
Which brings us back to that energy footprint. This immense power clearly comes at an immense environmental cost. Let's talk about that carbon question because it's a big worry for a lot of people.
It absolutely should be. Yeah, these GPUs, they consume electricity like crazy, like elite athletes guzzling energy drinks, but constantly. Training just one large model, like a GPT-3 size model, just once. The estimated carbon footprint can be more than, say, flying across the Atlantic hundreds of times. It's staggering. And that's just the training, the day-to-day use, the inference. When millions of people are asking questions, that ongoing cost can actually add up to more than the initial training cost over the model's lifetime.
Wow. Okay, so what are researchers and the big companies actually doing about this? Is anything changing?
There's definitely more focus on it now. Researchers are starting to benchmark efficiency, not just how accurate a model is, but how many joules of energy it takes per token generated. People are actively developing and deploying those efficiency techniques we mentioned. Quantization, making models sparser, using compute more adaptively, and importantly, sourcing renewable energy for the data centers. But yeah, every flashy new demo, every capability jump, it still carries an energy price tag. And users, I think, deserve more transparency about that cost. It's also true that the companies with the deepest pockets and access to greener power grids can afford to run those massive experiments more easily, maybe without as much public backlash over the carbon cost. That sometimes explains why one lab suddenly leaps ahead. It isn't always a single algorithmic breakthrough. Sometimes it's just they had more silicon acreage humming away on clean energy.
Right, access to resources makes a huge difference. So, okay, you've got the hardware, you've
Yeah.
got the software. How do you actually train an LLM? What's the recipe?
Ah, the training recipe. Yeah, anyone who works with these models knows the sort of holy trinity of training. Three main stages. Stage one is pre-training. This is where you just feed the model that mountain of raw text we talked about, the internet, books, code, everything. You basically let it learn by playing a massive game of fill in the blanks, predicting missing words or tokens. This is where it gains its broad knowledge about the world, about language, about facts. It makes the model knowledgeable.
Okay, so that builds the foundation, all the raw knowledge. What comes next?
Stage two is supervised fine-tuning, or SFT. Here, you switch gears. Instead of just raw text, you show the model-curated examples. These are typically high-quality examples of question-answer pairs or instructions and the desired responses. This step teaches the model how to follow instructions, how to answer questions helpfully, how to adopt a specific style, like being a helpful assistant. It teaches it, you could say, style and helpfulness.
Got it. And the third stage. This is where humans get more directly involved in shaping the behavior, isn't it?
Exactly. Stage three is often reinforcement learning from human feedback, usually shortened to RLHF. This is quite clever. You have the model generate several possible answers to a prompt. Then you have actual humans rank those answers from best to worst. Based on thousands of these human rankings, you train another smaller model called a reward model to predict which kinds of answers humans prefer. Finally, you use that reward model to further tweak the main LLM using reinforcement learning techniques, essentially guiding it to produce answers that will maximize that predicted human preference score. This stage is all about teaching the model manners, making it safer, more aligned with what users actually want, making it less likely to say harmful things, for instance.
So, pre-training for knowledge, fine-tuning for style and helpfulness, and RLHF for manners and safety. What's the end result of putting a model through all that?
Well, the goal is to get an assistant that's knowledgeable, helpful, generally follows instructions, tries to be harmless. It's why modern chatbots will usually refuse to give you dangerous recipes, why they might sometimes say, I don't know, instead of just making stuff up, and why they can often cite sources if you ask them to. It's the result of that whole three-stage process.
It really sounds like the data you feed it at every stage is absolutely crucial then.
Oh, data is everything. It's the invisible engine driving the whole thing. High-quality data is the unsung hero behind basically any LLM success story. You start with huge web scrapes, digital books, Wikipedia, code repositories, news articles, multilingual text. It all goes into the mix for pre-training. But it's not just about sheer quantity. Quality is maybe even more important. Engineers spend a huge amount of time cleaning the data, removing duplicates, trying to balance different viewpoints or topics, and filtering out toxic or harmful content. They also actively work to combat bias, trying to include more diverse perspectives, reinforcing neutral language styles during fine-tuning, because ultimately the model is only going to be as good, as fair, and as knowledgeable as the data it learned from. You can think of the data as the real intelligence source, perhaps even more than the model architecture or the parameters themselves.
So, just having more and more data isn't necessarily the answer. Bigger isn't always better.
Definitely not. A massive data set, say 10 trillion tokens, but filled with low-quality spam, hate speech, or just conspiracy theories, that could actually poison the model, make it worse, not better. Modern LLM teams invest heavily in data curation, data cleaning, data sourcing. Some even generate synthetic data now using one AI model to create high-quality training examples for another model specifically to target weaknesses, like improving reasoning or math skills. Data quality is paramount.
Okay, this is fascinating. Now, I'm trying to really picture this training process happening, this marathon, on all those GPUs you mentioned. Can you help me visualize that? It sounds incredibly complex.
Yeah, let's try an analogy. Imagine you have a gigantic crossword puzzle, okay, like the size of a football field, and every square needs a letter. Your goal is to fill that grid as fast as possible, because once you solve it, you unlock the next giant crossword and the one after that. Thousands of them. Now just swap the letters for numbers, those floating point numbers representing model parameters and activations, and swap the crosswords for billions and billions of token predictions. That gives you a rough sense of the scale and the task involved in training a big LLM.
Okay, giant number crossword. I like that. So, how do the GPUs actually tackle that enormous puzzle?
Right, so a single GPU is like one very fast worker. It can handle maybe a few rows or columns of your giant crossword incredibly quickly, but the whole puzzle is way too big for just one worker. So what the builders do is they line up thousands of these GPU workers in big racks. They connect them with super fast networking, like high-speed fiber optic cables, and then they give each GPU worker a portion of the puzzle to work on simultaneously. Maybe one group of GPUs works on the first few rows, another group works on the next few rows, and so on. In the machine learning world, this is called data parallelism. Each GPU processes different batches of training sentences, calculates the necessary adjustments, the gradients, and then they all send their findings back to a central coordinator which averages everything out to update the main puzzle solution.
Okay, data parallelism. Got it. But what if the puzzle itself, the model, is just too enormous to even fit onto one single GPU worker's desk, so to speak, even with data parallelism?
Great question. That happens with the really huge models, the ones with hundreds of billions or trillions of parameters. The model itself is too big for one GPU's memory, so they use another trick called model parallelism. They actually slice the network itself across multiple GPUs. Imagine layer 1 of the neural network lives on GPU A, layer 2 lives on GPU B, layer 3 on GPU C, and so on. The data flows through this pipeline, gets processed by layer 1 on GPU A. The result gets passed immediately to GPU B for layer 2, then to GPU C for layer 3, like an assembly line. So the data chunks stream through these layers distributed across many GPUs. Each step, each hop between GPUs takes tiny fractions of a second, but it happens billions upon billions of times during training.
Wow. So it really sounds like having a bigger fleet of GPUs just directly translates to faster training. That must be a massive competitive edge.
It absolutely is. Training speed really boils down to maybe three main things. One, compute muscle. Just having more GPUs means you can do more calculations per second. Simple as that. Two, interconnect bandwidth. Having really fast connections between those GPUs is crucial. If the connections are slow, the GPUs spend time waiting around, gossiping about gradients, instead of working. And three, software finesse. Clever software libraries like DeepSpeed or Megatron are needed to manage this incredibly complex orchestra, keeping all the GPUs busy, efficiently managing memory, maybe using techniques like mixed precision math to speed things up. When you hear about OpenAI renting tens of thousands of NVIDIA H100 GPUs, that investment directly allowed them to take a training run that might have taken 6 months and shrink it down to just a few weeks. So companies with bigger GPU clusters can simply try more ideas, iterate faster, find and fix bugs quicker days instead of months or quarters. In AI research, that iteration speed is absolutely critical to its survival. And that fundamental reality explains a lot about why only a handful of giant companies are truly leading the charge at the absolute cutting edge. It's often less about having one single secret algorithm and more about having the sheer capacity for incredibly rapid experimentation and learning.
That makes total sense. Okay, let's shift focus a bit to what these models can actually do now. Thinking about the breakthroughs, say, from 2023 through maybe early 2025, what capabilities should we expect from current LLMs that might really surprise someone who hasn't been following super closely?
Right. By now, if someone asks, what is an LLM, they probably expect more than just, basic chatbot conversation. The expectations have risen. A big one is long memory or large context windows. Models like Google's Gemini 1.5 Pro or Anthropic's Claude 3 can handle context windows of 1 million, even 2 million tokens now. That's like feeding it an entire novel or a massive legal document or hours of video transcript, and it can reason about the whole thing without losing track of the details from the beginning. That's huge. Another key area is visible reasoning. Some models, like Claude 3.5 Sonnet, are getting better at showing their work, revealing their chain of thought for how they arrived at an answer. This is critical for transparency and trust, letting you actually follow the logic.
Yeah, being able to see the steps is incredibly important, especially for complex tasks or checking for errors. What else stands out?
Multimodal fluency is a really big one now. Models like GPT-4o, for example. It doesn't just process text. It can listen to your voice in real time. It can speak back naturally with different tones. And it can see and interpret images or video feeds simultaneously. So you can have a spoken conversation with it where you point your phone camera at something and it reacts to what it sees, or it can watch a video and summarize it for you. That integration is becoming much smoother. And related to that is tool use or agentic behavior. Models like ChatGPT can now effectively use tools. They can call external APIs, run Python code to perform calculations, browse the web for current information, all sort of seamlessly within the flow of generating an answer. It's like having a research assistant that can actually go do things for you, not just talk about them. Plus, just raw speed, faster inference. We're seeing models like the Flash series from Google or Anthropic's Haiku that can generate hundreds of tokens per second. This makes the interaction feel much more immediate, less laggy. All these upgrades, longer memory, better reasoning, multimodality, tool use, speed, they're constantly redefining what we mean when we try to explain large language models. The goalposts are always moving.
Okay, so putting it all together for our listeners, if a colleague comes up to you tomorrow and asks, hey, remind me, what is an LLM again? What's the confident, concise answer you can give them now?
I'd say an LLM at its heart is still basically an incredibly sophisticated autocomplete system. It's trained on a massive amount of human text and code. Its core job is predicting the next piece of text, the next token, with remarkable skill. But then it's been carefully fine-tuned using human feedback to be helpful, harmless, and honest. And now the latest versions can also understand and generate images, respond to voice, and even use external tools to get things done. So, no, it's not a thinking brain like ours, but it can definitely act incredibly brainy in many useful ways.
That's a great summary. And looking ahead then, peering into a crystal ball just a little, what should we expect next? Where are LLMs heading?
Well, the trends seem pretty clear. Expect them to keep getting leaner and faster, more efficient. Also, hopefully more truthful, with fewer hallucinations. And definitely greener, as efficiency improves and more renewable energy is used. We'll likely see more specialization. Instead of one giant model trying to do everything, you might have an LLM highly optimized for, say, legal document review. Another one focused specifically on scientific research, like protein folding. Maybe another designed purely for real-time, natural-sounding voice translation. They'll probably all share that same underlying transformer DNA, as we called it, but they'll differ quite a bit in their specific training data and fine-tuning, optimized for their particular job.
Which means that for all of us, just understanding these systems, having some LLM literacy is going to become even more important, right?
Oh, absolutely. As these models become more embedded in our work, in our tools, and society, that literacy is crucial. You need to know how to interact with them effectively, how to write clear prompts to get what you want. You need to maintain a healthy skepticism, always be ready to check citations, question confident-sounding claims, especially on important matters. And it's always worth remembering where their knowledge comes from, human text. That means they reflect all the amazing brilliance found in human writing, but also, inevitably, our biases, our blind spots, and our flaws too.
So keep asking, what is an LLM? Keep learning, keep refining that understanding. Because it feels like as these models keep evolving and that definition keeps shifting, every single update is nudging us closer to machines that feel, well, less like simple tools and maybe more like complex teammates.
That's a good way to put it. And whether that future, that closer collaboration excites you or makes you nervous, understanding how we got here and where it's going, that's really the essential first step if we want to have any hope of steering it in a direction we actually want.